Thank you for coming to my graduation talk. I have to admit that I've given many talks before, but it's the first time in a decade that my mom is actually coming to a talk. So I'm really nervous. I titled the talk like I titled my thesis, Visualizing Regular Tessellations, Principal Congruence Links, and Equivalent Morphism from Surfaces to Free Manifolds. The talk will probably go until like around here. I structured the talk as follows. So the first half of the talk will address the question, what is a tessellation? Then what is a regular tessellation? And then what is kind of the best tessellation we have in two-dimensional geometries? And then there will be a 10-minute break with an outdoor activity involving a sculpture outside of this room. And then we will conclude this talk with a 15-minute part which will transfer the first half of the talk to 3 dimensions. And then the last part of the talk will show 2 drawings. The essence of the talk is this. We are really attracted to highly symmetric objects. And you can make this term of highly symmetric, you can quantify it in a very mathematically precise sense. And then for 2 of these most beautiful objects in 3-dimensional hyperbolic geometry, I was actually able to draw pictures. So some of this like nice mathematical abstract beauty actually descends to something we can visually enjoy. And that's the 2 pictures. They will appear again at the end of the talk. And this object here is very symmetric. It has 1,296 symmetries. This object here has 2,880 symmetries. They are very symmetric. In fact, no other hyperbolic object can have more symmetries per volume or area than these 2 guys. And this idea of having like most symmetry per area or volume is like central to the talk. It will reappear several times, even in unexpected ways. For example, it will tell you why the herpes virus shell looks the way the herpes virus shell looks like. The goal of the talk is to make you understand these 2 pictures and understand why I'm so proud of them. I mean, each one took me a couple of months to draw, and it was kind of a journey to get to them. And 6 of the symmetries here you can directly see in the picture. Like you can like take this and then just flip the paper plane around, or take this and rotate the paper plane 120 degrees. But most of the symmetries, unfortunately, can't directly see. And after this talk, which is a journey from 2 dimensions and Euclidean geometry to 3 dimensions and hyperbolic geometry, I hope you have a much better idea what these pictures mean, and you can appreciate these pictures. And you cannot just appreciate the black stuff, the link here, but you can actually appreciate the stuff which is not the black link, the white stuff, the stuff surrounding the link, the complement of the link. Because that is really interesting stuff. That is the space which has these 1,296 symmetries. So that's the goal of the talk today. Let's start with the first question. This is a tessellation, and a tessellation is a partition of a surface, or later of a space, of a 3-dimensional space, into polygons and polyhedra. So when you like came up to this beautiful building and walked into the door, you all actually saw tessellations probably around you. Like, for example, like on the street, you would see this tessellation by rectangles. When you walked through the entrance door, you would actually see this Penrose tiling, which is the tessellation by rhombi, where each angle here is a multiple of 36 degrees. And in order to make up the Penrose tiling, there's some additional rules, like you're not supposed to do something trivial and use only 1 tile. And if you apply these like additional rules, then you get actually a tiling which you can make infinitely large. It can cover the entire plane, but it will never repeat itself. It's kind of the opposite of what a regular tessellation is. I'm so happy that Martha flew in today. So that's my office in Maryland. And she gave me actually those tiles. I think Christian enjoyed playing with them as well. I think this is Christian's.
The outdoor activity will involve this sculpture that also shows a regular tessellation.
This sculpture is called The Eightfold Way by Hellman Ferguson. It depicts the Klein quartic. It's a tessellation by actually heptagons. So if you're outside, then one of your homeworks will be to actually count that it has 7 vertices. It's a very beautiful tessellation. Beautiful in the sense that it's again a tessellation where no other tessellation can have more symmetries per area than this one. This time, hyperbolic 2-dimensional. You don't know quite yet what hyperbolic area is, so there will be Escher pictures later in the talk, which will hopefully give you a sense of why this is such a beautiful tessellation. And I have a very personal connection to this because where one of my friends in the CS department, Professor Carlos Simpson, he actually came up with the Planck boarding and said, Matthias, I want to understand this, and I want to figure out how I make sculptures of this surface and the next surface in this family, the McBeach surface of Team 7, and so he got me started in this. And I mean, this thing was really at the epicenter of where all my research went, because when I started looking at that, I wanted to understand more hyperbolic geometry, and when I asked Ian about it, Ian had this interesting construction of a 3-manifold, and that's kind of how half of the research of my thesis really got started. Let's go to the next question. So I showed you what tessellations are. What is a regular tessellation? And I'll do this at kind of the easiest example of a regular tessellation you can imagine. This is graph paper, so you just tessellate the Euclidean plane by squares. And then the defining property of regular tessellation is that if you are a person living inside that regular tessellation or on that regular tessellation, then you cannot tell through intrinsic measurements on what tile of a tessellation you're standing on or at what edge of that tile you're looking at. That is the defining property of regular tessellation. So here's an example. This is a regular tessellation made out of Legos. So this is Lego Man, and he's standing at 3 different spots here. So here he's standing in the same tile, but looking at 2 different edges, and here he's at 2 different tiles, but looking in the same direction, kind of. And this is kind of the outside view on Lego Man at these 3 different spots. But the inside view of what would Lego Man actually see is always the same. It doesn't matter on what of the 3 spots he stands, he always sees this picture. And that is because the tessellation is regular. This is the defining property of regular tessellation. You can not just tessellate the Euclidean plane, you can also tessellate the sphere. The sphere is kind of a very important object. For example, the surface of the Earth is a sphere, so if you do any navigation, if you want to draw maps, you need to understand the topology of the sphere. Traditionally, kind of regular tessellations of a sphere were drawn as actually tessellations of a sphere, but as solid, as a polyhedron. So here, for example, you have a cube, and it's solid, kind of and then you take the surface of the cube and you balloon it out, and when you see that, you get a tessellation of a sphere by the spherical squares. And from a topological point of view, and I'm a topologist by heart, the 2 pictures are the same. I mean, you don't care about ballooning it out. So for me, the cube as solid and the cube as regular tessellation are the same. And to make sure you really understand what a regular tessellation is, I want to also tell you, give you an example of what is not a regular tessellation. This is the bipyramid. It has 6 faces, which are all triangles. And if you look at this vertex, and this vertex has 4 edges to it, but this vertex has only 3 edges to it. So this vertex and this vertex are different. And that also means that you can actually distinguish this edge here which has two vertices with 4 edges to it, and this edge here, which has the vertex with only 3 edges to it, we can distinguish these two edges. And that means that if Lego man would actually live inside this regular tessellation, then Lego man could distinguish these two edges easily by just counting how many edges we need at a vertex. So this is obviously not regular tessellation. And more generally speaking, it's a necessary condition for regular tessellation that every polygon has the same number of edges, and that every vertex has the same number of polygons meeting at that point. It's a necessary condition. It turns out it's not a sufficient condition. And I will give a counterexample later why this is not a sufficient condition. And this is kind of the oldest mathematical result in my talk. This is over 2,000 years old. This is Greek. These are the 5 Platonic solids. The 5 Platonic solids are really a classification result of the regular tessellation of the sphere. And there are 5 Platonic solids: the tetrahedron, the cube, the octahedron, the dodecahedron, and the icosahedron. There's one guy I want to point out, which is the tetrahedron. The tetrahedron is the simplest Platonic solid in the following sense, that if you pick 2 points on the span in a line segment, if you pick 3 points, then you get a triangle. So the simplest polygon you can create is a triangle, because if you have less than 3 points, then you can get a line segment. And similar, the simplest solid you can make is spanned by 4 points, and then that's exactly what you got with the tetrahedron. And because it's so simple, the tetrahedron is
an important building block for all kinds of three-dimensional spaces.
And it will also appear later in the talk, because this is the guy the link complement is made out of. There's one important concept. So, if you remember Lego Man, when Lego Man was like standing at these different spots, and you can apply a transformation to the regular tessellation. You can apply a transformation to the Euclidean plane, where you rotate it or move it, and if that transformation preserves the regular tessellation structure, if you end up mapping each square again to a square and each edge to an edge and each vertex to a vertex, then you call that a symmetry of regular tessellation. The symmetries of regular tessellations come in 2 flavors, and 3 dimensions, or 2 dimensions, I call them rotational symmetries and mirror symmetries. More generally, we would call them orientation preserving and orientation reversing symmetries. And here's an example of a rotational symmetry. So you have this axis here, which is going to one face center and one vertex of the tetrahedron. So you have this thing, and if you imagine you take this axis and then you rotate the entire tetrahedron by 120 degrees, then you actually get back the same picture. And that means that this 120 degree rotation is a rotational symmetry of the tetrahedron. And it would, if you apply this, then the Lego man would move from here to this spot. So Lego man standing here would see the same picture when Lego man standing here, because there's this 120 degree rotational symmetry. And the tetrahedron has in total 12 rotational symmetries. One of these transformations is trivial because it just takes the tetrahedron and leaves it in place. So one is just the identity. But 11s are non-trivial, and you count all of them to have a group of symmetries. So it has 12 symmetries. And then on top of these 12 rotational symmetries, there are actually 12 mirror symmetries. So mirroring is the transformation which takes an object and takes it to a mirrored object. You're all familiar on how the object and how the mirrored object looks like, because there's this device called mirror, which
how does that work?
which actually takes you and produces your mirror copy. it does not really produce a mirror copy. The mirror only it only bounces off photons. So what you really get is a virtual image of your mirror of your mirror copy. So that means that you have a window into the mirror world. You know how your mirror object looks like, but you cannot shake hands with yourself. And in order to specify this mirroring transformation, you need to specify a plane, which is like the mirror plane. If an object stays invariant under mirroring, then you call that a mirror symmetry. So the tetrahedron, for example, has this mirror symmetry about this plane. The points which intersect the plane are fixed. So in particular, these two vertices of a tetrahedron would be fixed, and these two vertices would be interchanged by this mirror symmetry. And then this is one particular mirror symmetry, and when you have 12 such planes, you can draw through a tetrahedron. So you have in total 12 mirror symmetries of the tetrahedron. And in fact, all the Platonic solids have as many mirror symmetries when they have rotational symmetries. So now that you understand what symmetry is, let's go back to the Platonic solids and count the number of symmetries. So a tetrahedron has 12. Then you have the cube and the octahedron. They both have the same symmetry group. The rotation symmetry groups have order 24. For mathematicians, the rotational symmetries of this guy are A4, here they're S4 and S4, and here they're S5 and S5. And then you have two objects which have actually 60 symmetries. So this guy here is kind of the guy with the most symmetries. Why do we care? I mean, you can also think of this guy has the most symmetries per kind of surface area of the sphere. But that also implies that kind of one of these tiles is as small as you can get for regular tessellation of the sphere. And that's important for some applications. For example, assume you're a virus and you're competing with other viruses, and you want your genome to be as small as possible, so that you have a competitive advantage over other viruses. That means that the proteins you want to build are as small as possible. But you can use your host cell to kind of make arbitrary many copy of the same protein you need. So if you want to build a virus shell, then it's best to use a very symmetric virus shell so that you can use the same tile and just make many copies of them, and therefore you can make the tile as small as possible. And the best way to do it is to use the icosahedron. So at some point, evolution figured that out, and there are actually viruses which have the icosahedral capsid. This is, for example, the cytomegalovirus. I estimate that if 3, 7, 10, 12, 13 people in this audience, so I expect that around 6 or 7 people actually have a cytomegalovirus. It's an opportunistic virus which like half of the population has. It was also like Tuba's favorite virus. Then the next virus, actually, the human simplex virus, also has the icosahedral capsid. That's the virus causing most spread. It's actually transmitted disease, herpes. And then there are actually many more viruses which have icosahedral capsids. So this really appears in nature. There is another thing here. We tend to find faces with a mirror symmetry more attractive. I think I made my point. I showed you graph paper, and when I showed you 5 Platonic solids, all these regular tessellations have a mirror symmetry. So you might wonder whether it's just by accident, or whether it's always like that. So natural question is, are there actually regular tessellations without mirror symmetry? And the answer is yes, and I will show you one. I will show you a regular tessellation which does not allow mirror symmetry. But before I can do that, I need to tell you how to construct regular tessellations of surfaces which are a little bit more complicated than just the sphere or Euclidean plane. And we do that as follows. You start with graph paper. Then you pick a square in that graph paper, such that all the four vertices of that sphere lie on grid points. If you have that, you take this 3 by 3 square, and I didn't trace all the lines because it was very confusing. You take this 3 by 3 square, you start bending it, bend it a little bit more, and at some point you can bend it so far that you can glue together two of the sides of that square. You get a cylinder. Then you start with the cylinder, and you bend the cylinder, you bend it more, and eventually you can glue the two ends together, and what you get is this torus. Torus is a mathematical name for like the surface of a donut or a bagel. I kind of didn't trace the regular tessellation structure through with like the 3 by 3 square grid structure. So here's the regular tessellation structure on the torus. You see that we have like 3 by 3 squares living on the torus. And that's the regular tessellation of torus. Let's see how a person who's living in this tessellation, what he would see. So the thing is that in order to get the geometry and all this right, we also need to think that the light rays of Lego man are bent, right? We're bending like the regular tessellation all the time, so we also need to bend the light rays appropriately. So Lego man's light rays would also like bend, and in fact this like eye ray of Lego man would like loop around and would hit Lego man's back. And that means that if from the inside view, from Lego man's inside view, Lego man would see a copy of himself 3 squares forward. And then of course he would see another copy of himself, another 3 squares forward, another 3 squares forward. But then the light ray can also go this way, so he also sees like another copy of himself 3 squares to the left and so on. So this is Lego man's inside view of a regular tessellation. The tessellation would look to him like square paper. So nothing new there. But the difference between Lego man living on graph paper and Lego man living on like this 3 by 3 square torus tessellation is that he would see infinitely copies of himself. A copy of himself appearing after 3 squares. There's one thing, I started with a square. If I had not started with a square, I would not get a regular tessellation. Again, to make sure you understand what regular tessellation is, let's do an example of what's not a regular tessellation. Let's take this 3 by 4 rectangle and glue it together to a torus, and then look at the inside view of Lego man. And look at the feet with respect to this arrow. So it was turning a couple of times at 90 degrees, and if you didn't catch it, here's the Lego man's view in one direction, and when he turns 90 degrees, and gets this view. And here you see when he goes 3 steps forward, he sees a copy of himself. Here goes 4 steps forward, he sees a copy of himself. So Lego man's view looking this way and Lego man's view looking this way are different. And that means that the property of being a regular tessellation is violated. This is not a regular tessellation. So here's another way of seeing that it's not a regular tessellation. This is Lego man. He puts down a marker, and like Ariadne, like from Greek mythology again, like Ariadne in Minos labyrinth, she like starts like taking a thread from and tie it down. So he ties down a thread to this marker here he put down in the square, and then he starts walking. And he walks through 3 squares, and when he's back to the original marker, and the thread closes up, and let's say he used the red thread, then that's the inside picture of him now. He used this red thread, went 3 steps forward, the thread closes up, and he gets 1 thread. Now, he turns 30 degrees and do the same thing again. This time he uses the green thread, walks around. He does 4 steps, and the green thread closes up. So now he has this picture where he has a red thread and a green thread. The red thread would have length 3 squares before it's crossing, before it's closing up. The green thread would have length 4 squares before it's closing up. But now he knows that he can distinguish this edge from this edge because he has a way of measuring distance, these like how long to walk before something closes up. So he has actually a way of spinning these threads and distinguishing these 2 edges from these 2 edges of the square. So these 2 edges are really different, and you can distinguish them through intrinsic measurements, and therefore it's not regular tessellation. But notice that this regular tessellation has only squares, and there are always 4 squares meeting at a vertex. So locally, if you were only taking this part, or you would only take this part of regular tessellation, of this tessellation, it would look like a regular tessellation. But globally, it's not regular tessellation. So earlier when I said that this is a condition which is necessary but not sufficient, this is exactly the case where you see that it's not sufficient. Now that you understand how to take a square and how to turn it into how to take a graph paper and how to turn the tessellation of a torus, we can actually turn this into classification. So we can classify all regular tessellations of the torus by squares. And actually there are 2 more families of regular tessellations which work analogously. And when we have classified all regular tessellations of the torus. If we have such a square, then you can do the following. You can take 2 vertices on an edge. You can count how many horizontal steps you go, and you can count how many vertical steps you go. So you go 1, 2, 3 horizontal steps, but no vertical steps. And here you go 1, 2, 3 horizontal steps and 1 vertical step. And then you can encode that as a complex number. So in this case, you just write 3. And in this case, you would write 3 plus I for like the 1 horizontal or the 1 vertical step. That's I hope one of the few math jobs I guess a complex number. And then you notice that you have a choice here with which edge you start.
So you can write 4 complex numbers to encode the same regular tessellation. They are related by multiplication by a power of I. In math terms, they span the same ideal in the ring of Gaussian integers.
And this example on the right side, the 3 plus 1i example, that's an example of a chiral regular tessellation. It's a regular tessellation which does not allow a mirror symmetry. It's a mirror symmetry for regular tessellation, unlike the Platonic solids I had earlier. And how do you see that? Let's assume that Lego man woke up in this regular tessellation, and kind of like me, he forgot in the morning which hand is your left hand and which hand is your right hand, and he wants to figure it out. This way he can make a measurement in order to figure out which side is left. So he wakes up in the tessellation 3 plus 1i. He forgot which hand is his left and which one is his right hand. So he puts down a flag, a marker, in 1 square. Then he makes 3 steps forward, and then the flag will be to his left. So he now knows that his left hand is left. if poor Lego man had woken up in the tessellation 3 by a 3 by 3 square, Lego man would have a problem. He could not figure out where left and right is. Because this tessellation allows the mirror symmetry. I mean, you can take the square and just mirror. And therefore, there's just no way he would ever figure out where left and right is. He's like lost forever. It's a very interesting question now, whether our universe is like, you know, what class our universe falls. You know, is there any law in nature which would actually distinguish, you know, what's your left and your right hand is? So I have an example here I have some examples from biology. So here is the Greek word for hand, and chirality means handedness, and an object is chiral if it does not have mirror symmetry, and it's amphichiral if it has mirror symmetry. And there are actually molecules in nature, in life, you're made out of. Each of them has a couple of billion of those. For example, DNA is a chiral molecule. And alanine, the second easiest kind of amino acid, is also chiral. There are also amphichiral molecules in life. For example, water clearly has mirror symmetry here, or glycine. This is the easiest amino acid. The residue is hydrogen. It's a funny incidence that is everywhere you go in nature, you will always find DNA of the same handedness. At some point, evolution has decided to prefer one-handedness of DNA over the other-handedness. And every creature on this planet uses this DNA. Every creature uses this form of amino acids. And nobody has ever found any living thing on Earth which uses different handedness. And thank you, Marisana, for coming, because I'm playing a little clip of a show you once got me tickets for.
Excellent.
Yes.
And Marcello says if you look at pebbles or granite or cement, inanimate stuff, when you look at the shape of things inside, it's a mixture of the two.
50% left-handed, 50% right-handed.
However,
if you look at all the proteins of living things, they're always left-handed and no right-handed at all.
Really?
Life has chosen one over the other. Life as we know it has
You mean when scientists look inside of living things, they always see it, the molecules are pointing one way?
Yeah.
Right. So somehow, and this is what's really amazing, somehow life is choosing a very specific shape for the molecules to make up stuff.
That's correct.
when you say life has chosen, let's take that sentence apart. Life meaning everything that we know of on Earth, every living thing.
Hence my phrase, life as we know it.
Everything.
That's what that means.
The littlest things to the blue whale.
That would be as we know it.
The littlest, teeniest thing to the tree, the biggest tree, the giant sequoia.
That would be as we know it.
Huh.
Every protein in you, dogs, trees, you name it.
Is filled with left-handed building blocks?
Yes. It's called the chirality of life.
The chirality of life. Life, my friend, is left-handed.
That's pretty... That's, well, it feels cool, but let me just, like, so what?
So they have a bunch of funny examples now coming up of like taking sugar, taking mirror sugar, and mirror sugar tastes very different than sugar and stuff like that.
Can you digest it?
I think you can still digest it. There's a very dramatic example coming up. Wait for 10 more seconds. So here's the chiral tessellation again, and this is the mirror image of the chiral tessellation. The difference doesn't look that dramatic. In biology, there also are some molecules which come in one way, and they also come in the mirror image. Mirror sugar just tastes different. It won't kill you. This is thalidomide. It's a drug that was used in the late 1950s till the very early 1960s, produced by a German pharmacy, a The German brand name is Contergan. And thalidomide restricting Contergan comes in two-handedness. The left-hand side works as a sedative and was given to pregnant women in the late 1950s. The mirror image of this molecule has the unfortunate ability to bind to DNA and block certain promoters, which would be necessary for building blood vessels, and it would cause severe deformities in over 10,000 children in the 1950s and 1960s. It was one of the biggest scandals in the pharmaceutical industry of the 20th century, and caused a lot heavy regulation after that. I switched to a light topic. I told you how to tessellate the Euclidean plane. I told you how to tessellate a sphere, but we went to tessellate the surface of a donut, the torus. Let's go to higher surfaces. Something more complicated. And can we find regular tessellations on these more complicated surfaces? And the answer is yes, but I first need to tell you what hyperbolic geometry is. I will not try to write it down to the metric and the isometry group. I'll just show you a picture. This is a picture by my MC Escher, one of my favorite artists. It shows devils here and these angels. They really naturally live in a hyperbolic plane. Problem with visualizing a hyperbolic plane is it's like the same when you open an atlas of the Earth, that if you try to take the entire surface of the Earth and you push it down into one road map, you're forced to distort something. So either you don't get the angles right, or you don't get the area right, or you don't get the distances right. Something in the map will be a little distorted. And the same here. So this is a projection of the hyperbolic plane into a disk, and it's such that the angles all look right. So you see that this angle, the pointy angle here of all the devils, the things looks the same, but the sizes are not the same. So all these devils really are the same size, and they all are the same geometry. They're all indistinguishable. It's just that in this projection of the hyperbolic plane into the disk, they appear in different sizes.
So is this supposed to be like a dome we're supposed to think of as being projected onto a two-dimensional surface? Or
either you kind of think of it as a saddle surface, but that only works up to a certain point, and then the saddle kind of goes to different curvatures. That's like the result by Hilbert, that you can embed the hyperbolic plane into our plane. Or the nicest model is to think about it in the Minkowski space as a hyperboloid. But for drawing purposes, the concrete is the best way of working with hyperbolic plane. There's another thing that will come up in the second half of the talk, that these guys, the angels and the devils, are complementary. So the nice thing is that if you draw the devil in black, then the white stuff is the angel. It's nice that Escher had this nice mathematical concept of what needs to be complementary, But then he also paired it with this philosophical concept of angels and devils.
Wait, I forgot. It's supposed to have finite volume?
Each rock has finite volume. The disk has infinite volume. The density gets really, really steep. So if you shoot a light ray, then it would get slower, so slower would never hit the boundary. So remember that I was taking the Platonic solids and I was ordering by a number of symmetries, and we can do the same thing with hyperbolic tessellations and take hyperbolic tessellations of different kinds. Here's by pentagons, and here's 1, 2, 3, 5 meeting, and here's And then you can wonder how much symmetry you have per area, so to speak, or like how large is the tile. And you see that actually this one, the one with heptagons, the three heptagons lead to a vertex, is the one which has like the smallest area you need for symmetry to have. Kind of. This is the heptagons are pretty small compared to these pentagons. This is the tessellation with most symmetries per area. And there is a connection to the sculpture outside. Namely, the way you got from graph paper to the torus by cutting out a square and gluing the ends together. The same thing you can do here. You can cut out the domain here, glue it together in the right way, and then what you get is the Klein quartic. You get the surface of a sculpture which is standing outside.
Why exactly is it? I mean, couldn't you have just made the heptag? I mean, okay. I guess the fundamental question is the two shapes on the top. It looks like you're taking the shape and put it in the middle, and the other one is sort of slightly off center.
Oh, yeah.
Why is that happening? I mean, what's going on there?
Oh, sorry. That's because I screwed up when I copied the picture from Wikipedia. But the vertex centered and not the face centered one.
Okay.
Yes. There's like a hyperbolic transformation where you can move forward stuff around. Yes.
So in the top two, the edges are curved. Is that due to the projection? And
Yes.
inside the space, they are straight?
Yes. Inside the space, these are all straight. Yes.
And so how does scale come into the thing? I mean, if you say that this is the smallest size, the smallest shape that you can make a tessellation from an hyperbolic space, then how does...
There is a formula for hyperbolic area. So and if you compute the hyperbolic area formula for like the fundamental domain of this regular tessellation, this is really the smallest. But the nice thing is that here it also like visually is the smallest.
Can't you just make the length of the lines shorter and then make the other one smaller?
No.
No?
Hyperbolic space is kind of a little bit more rigid than Euclidean space. So in Euclidean space you have similarities and you can scale everything. Like you can take graph paper and just make every square twice as big. But it does not work for hyperbolic space. In hyperbolic space, if I tell you that this is the tessellation 7-3, so it has heptagons that meet at a vertex, then that specifies the geometry and it specifies how long an edge has to be. Good. So, having this picture, it's now time for the 10-minute outdoor activity. The sculpture is located behind this concrete wall there, and you have your exercises to do the following. You put your finger down at one of the vertices. You go take one way, and then imagine kind of your area in labyrinth, but you're a little drunk, so you go zigzag. So you go around an edge, like I do here. So you go around an edge, then you turn, stay right, then you walk one edge, then you turn left, walk one edge, turn right, walk one edge, turn left, walk one edge, turn right, walk one edge. And you do that with your finger on the sculpture. And if you do that 8 times, I claim that you're back where you started it. That's your homework for the 10-minute break. And when we meet here again at so far everything was 2-dimensional. I love 3-dimensional geometry and topology. So let's notch it up a little bit. We started with graph paper. Graph paper in one dimension higher would be this tessellation. You can tessellate free space, including free space, just using cubes. And one of the questions was like, I started with graph paper when I went to the Platonic solids, and I showed you what's the most symmetric Platonic solid, and you got the icosahedron, and it popped out as a symmetry group of the capsid of the cytomegalovirus virus. And then I showed you in hyperbolic case the 7-free tessellation. And you could use that thing to build the Klein quartic, which is the sculpture of the sign. So in 3 dimensions, and in Euclidean we had this discussion, like Ian asked, why does it make sense to ask what's kind of the most symmetrical spherical hyperbolic? Euclidean doesn't have curvature. So here the question doesn't quite make sense of what's the most symmetric tessellation. Now let's go to 3 dimensions and ask the same question: what's the most symmetric tessellation of a 3-dimensional sphere? And what's the most symmetric tessellation of 3-dimensional hyperbolic space? So let's start here. You get this guy. This is the 600 cell. It is made out of 600 tetrahedra. There's like, this is from Wikipedia, and there are a couple of vertices edges missing. Imagine that each point here has an edge which is pointed out, and there's next to a vertex at infinity. So this is the stereographic projection of the thing into free space, where one vertex is kind of a north pole. So there's like the thing I should explain. The Platonic solids were like called solids, right? So they lived in free space, but they're really regular tessellations of a 2-sphere, which is a 2-dimensional surface, maybe the 2-dimensional surface of a 3-dimensional ball. If you notch that up 1 dimension, then you have the 4-dimensional ball, and the 4-dimensional ball is bounded by a 3-dimensional sphere, and that 3-dimensional sphere you can project into our space using stereographic projection. So it's like in 2 dimensions. You just take a globe, you place it on a piece of paper, put a light at the North Pole, and it projects out. Same thing you can do in 1 dimension higher. And when you get that, you have the 3-dimensional sphere is our space plus 1 point at infinity. And this is how you can tessellate that free sphere by 600 tetrahedra, and that's the most symmetric way you can tessellate a 3-dimensional sphere. For hyperbolic space, the most symmetric thing, disclaimer, most symmetric ideal tessellation, is by, again, regular hyperbolic tetrahedra. So here's a little program I wrote during my last 2 years at high school. It's an OpenGL. I discovered that actually my graphics card has a very fast way of dealing with 4x4 matrices, and usually these 4x4 matrices were used for homogeneous coordinates to do computer graphics, but you can also use it to actually feed in matrices from SO3,1 and do hyperbolic geometry with your graphics card, and I thought it was really cool. So I wrote a little program to fly through hyperbolic free space. I think at this point I should really say many thanks to Dirk, because he really was like very, very influential. By the way, I compiled, after 10 years, I compiled this program onto Mac, and up to me needing to change the header files, the hash include, at 2 places that work out of the box. These vertices are very, very, very far away, and actually you see that this thing is tessellated. This is actually a horse sphere tessellated by triangles.
How many tetrahedra meet at a point at a green ball?
Infinite many.
Infinite.
How's that infinite? I mean, it can't.
Well, that's because they're ideal vertices. They're infinitely far away.
It's constant. I mean, I don't understand. I'm sorry.
So okay, let's try. Okay, it doesn't render the entire Bohr sphere, only renders part of it. Good. Here you have, so you're now kind of, so you saw this green thing, that's a Bohr sphere. I now navigated you inside the Bohr sphere, a little, pretty far out. So you see kind of the back of the Bohr sphere, and you see that it's Euclidean tessellation by triangles. If you want to watch more, there's a beautiful video called Not Not. You can just Google YouTube for Not Not and you'll find it. So you saw that this hyperbolic tessellation by heptagons of a hyperbolic plane, where like 3 heptagons would meet at a vertex. You could use that, and then you can construct the Klein quartic. The Klein quartic was kind of this finite surface bit. It started with this infinite tessellation, and then you got something which had only finite many heptagons. So now the question is, can you similarly take finite many hyperbolic ideal tetrahedra, which would usually tessellate all of H3, and take finite many and glue them together to get a regular tessellation? And the answer is yes. This is the only mathematical equation here. This is how you actually do it. This is a mathematical form which tells you how you glue finite many tetrahedra, hyperbolic ideal tetrahedra together to get regular tessellation. This is how my advisor Ian Agro wrote it down in a paper about the Klein quartic. But don't worry, I don't want to make understand what projective special linear group stands for, or what the Eisenstein integers are, or what the kernel of the map is. I think I rather draw a picture of it. And the question is, can you draw a picture of it? And I want to step back to 2 dimensions again. Let's assume you're a sphere person. You have lived your entire life on a sphere. You don't understand any other surface on the sphere. And someday somebody comes and says, can you understand a cylinder? And the sphere person says, yes, because the sphere person just removes 2 spaces from the sphere, and then the sphere person kind of like, you can take a zero out of points and you can bend it a little bit open and you get the cylinder. So if you're a sphere person, you can understand the cylinder. And if somebody would ask you to draw a picture of a cylinder and you're a sphere person, then it's easiest to just draw the complement of a cylinder. So if I draw you these 2 points and you're a sphere person, then you would understand that the complement is a cylinder and you would understand the cylinder. And now the question is, if I give you one of these hyperbolic tessellations by these hyperbolic regular ideal tetrahedra, can you draw a picture of it the same way the sphere person can draw a picture of the cylinder by removing 2 points? And the answer is yes, you can, but what is kind of the space you need to remove from our space in order to get it, in order to have that the complement should be distance to plus? What is the thing I need to remove from our space so that I'm left with a regular tessellation by regular ideal hyperbolic tetrahedra? And the answer is it's a knot, respectively a link. And a mathematical knot is kind of like knots you're used to, like the knot you used to tie your shoe or to tie your necktie. Just the difference that you want to glue the ends together.
In other words, a knot is a closed loop in space, but it can be embedded in an arbitrary complicated, in an arbitrary knotted way.
If you do it in a trivial way, you get the end knot, so this is the circle. If you have like, this is the easiest in terms of number of crossings. So this is the trackball knot, and then this is the next one, figure 8 knot, senkball knot. And then if you take several knots, or just unknots, just circles, and you link them together, then what you get is one approach called link. So chain is, for example, a link. It's like a 7-component chain. there's like a book on like how many mathematical knots how many mathematical ways there are to knot a necktie and stuff like that. Again, going back to nature, DNA is actually knotted, and there are actually several enzymes which act on DNA and change the topology of DNA. Like there's like they call DNA topoisomerases, and they actually take DNA and they kind of change the crossing of DNA. So that's knots and links, and if you remove the 12 component link, this guy, or 20 component link, this guy, from our space, then what you're left with is a tessellation by 54 respectively 120 regular ideal hyperbolic tetrahedra. And that was half of my PhD thesis coming up with two pictures. It's like a sequence of like a bunch of different covers. It feels like 40 pages worth of pictures to actually understand why this complement that 54 tetrahedra. Questions?
Those rings, do they correspond to the holes in the sculpture outside? Like the...
Yeah, so in order to get the analogy right, you kind of need to puncture we kind of drill little holes at the vertices of the sculpture. So kind of if you take the sculpture and you drill holes at each vertex, then that kind of Swiss cheese would be the ideal hyperbolic tessellation. And this is again the ideal hyperbolic tessellation. So you have these tetrahedra here, and the vertices of the tetrahedra, they're kind of chopped off and border this black stuff. So if you are inside this hyperbolic tessellation and you do the space flight I did, where you fly towards the green horse and you fly through the green horse here, closer to this ideal vertex, by that it would get closer and closer to this black thing. So you kind of imagine that this space gets dense and dense and dense across the black line, so that the light ray can never reach the black line itself.
The dot in the middle, what does that correspond to?
Oh, so in order to make it most symmetric, this dot here is the 12th component, and the nicest way of drawing the 12th component is just to imagine that we have a line sticking perpendicular to the paper plane out of this, and it's a circle which goes through the origin and through infinity on the S-sphere and goes up and okay. So I could have just drawn a link like that, but I didn't want to like destroy this.
So it's a link that it doesn't interact with anything else on the.
This thing links with 5 other components.
Okay.
Yeah.
So you've got 3 kind of rectangles on the outside, 2 inner triangles, and then 1/6 of the links, and then this dot.
Yes.
Those big components.
Yes.
Okay.
What's the application of this? Like,
it's very related to tons of areas of math which have tons of applications, but I didn't construct those applications in mind. So to be honest, I don't know of any application of this. I know that hyperbolic geometry has applications. I know that other regular tessellations have applications. I know that they pop up in nature and so on. I hope that this indirect link is motivation enough to study that.
Is this what a virus would look like in a 4D universe?
Yeah, in a hyperbolic three-dimensional universe, yes, exactly. That's how a virus would look like.
What is being optimized in the two, or maximized in the two different ones?
I'll try to. So this has a D6 symmetry. It has 6 symmetries. You can either rotate around the paper plane by 180 degrees around this axis, or you can rotate around 120 degrees by this axis. So I tried to draw a picture which has that symmetry and make it like as visually appealing as possible.
the other
And
one?
this one, yeah, this one is a little harder. So there's a twisting region here, and when you actually take this end and you glue it to this end, and you take this and you glue it to this end. So it's a, if you draw out the full link, it has a lot more crossings. And this one, if you think about, so this link really lives on a torus natively. So what you really do is that you take this region and then you bend it to, like you bend it and then you close it to a torus. And then if you look at this at the torus, then it actually is just kind of a wallpaper where this pattern repeats 20 times on the torus. So projected on a torus,
It actually has a 20-fold symmetry.